Okay. So, good evening, everyone. So, my name is Nilmoni Karak. I'm the official PMRF NPTEL TA for the course Fourier Analysis and its applications. So, today I will discuss some uh, problem related to your week 3 content. And there in week 3, yeah, so in lecture 11, they discussed the Poisson summation formula. Not sorry, the not the Poisson summation formula. This is Poisson kernel. Sorry. Then Cicero summability. And Phaser's theorem. Okay. And then Kroneker's theorem. And in last, Bell's equidistribution theorem. Okay. So there are I think 2-3 problems from Poisson kernel in assignment 3. So let us discuss this topic again. Okay, first I will discuss Abel summation and Poisson kernel. Abel summation and Poisson kernel. Okay, so first of all we take a series. Okay, given a series, the sum k equals to 0 to infinity ak. Yeah, so which may or may not be converge, which may or may not be converge, but bounded. Okay, not the series is bounded, but the corresponding sequence is bounded. Okay, for all k equals to 0. Okay, so we consider this. Now let us define AR by the sum k equals to 0 to infinity ak r to the power k. Okay, so yeah, so we define this. Okay, this infinite series, and okay, then now one thing, whether this series is well defined or not. Well, so now you have ak is bounded by this, and now okay, so AR, AR is actually, you just see what is mod AR. So this is basically less equals to your yeah, m times this sum k equals to 0 to infinity r to the power k. Okay, and this is less equals to your m times the sum k equals to 0 to infinity mod r to the power k. And when this series is well defined, or the series is converged, the series is convergent for your mod r less than 1. Okay, now also one thing, okay, if so AR is your what? AR is your yeah, k equals to 0 to infinity ak r to the power k. Now a1 minus, okay, so so this is a function of r, right? So we just taking a minus, so your a1 is not defined, okay, and a minus, that is basically defined by this limit r tending to 1 minus ar, and this is exist, right? If sorry, not exist, so we just, if we assume this exist, then we denote it by, sorry, a1, and a1 is your nothing but the series we considered first, ak, and this is like in the Abel sense. Okay, so for example, okay, for example, let us consider this series sum k equals to 0 to infinity minus 1 to the power k and k plus 1. Okay, but this series is basically does not fit in the above assumption, right? Because this is not bounded at all. Okay, so this sum basically 1 minus 2 plus 3 minus 4 plus 5 and so on. So yeah, technically this series does not fit in the above definition, but the power series, this k equals to 0 to infinity minus 1 to the power k, k plus 1 r to the power k, converges for mod r less than 1. Okay, and the sum is basically here ar, this sum one can find easily, so this is nothing but 1 by 1 plus r square. Okay, and yeah, so if you put here r equals to 1, then a1 is nothing but your 1 minus 2 plus 3 minus 4 plus 5 minus dot dot dot. This is nothing but 1 by 4 in Abel sense. sorry, sense. Now actually we want to apply this to Fourier series. Okay. Yeah, so we want to apply this in Fourier series. So let f belongs to L1 minus pi to pi. Okay, then so we consider a like integrable function over minus pi to pi. Okay, and now we define for 0 less equals to r less than 1, sorry, here f of theta f at n r to the power mod in e to the power in theta. Okay, okay, so actually we will show so that here f theta is nothing but 1 by 2 pi times f convolution PR of theta, and for some kernel PR. So yeah, in notes, so you just have seen this PR is denoted like this gamma r. Okay, okay, both are same. So okay, so how to show it? So AR f theta, this is nothing but n equals to minus infinity to infinity f hat n to the power mod n e to the power in theta. Okay, and now just use the formula for Fourier transform. What is the formula of Fourier transform? Minus pi to pi fx e to the power minus nx dx r to the power mod n e to the power I n theta. Okay, and that should be dx. Okay, and then so we can take outside this 1 by 2 pi, and also we can swap this integral because this is like convergent, and the yeah, at least this integral is convergent, right? So minus pi to pi fx and n equals to minus infinity to infinity r to the power mod n e to the power in, yeah, theta minus x is there, and dx. So basically yeah, how like we can swap this integral and sum, yeah, one can check this this holds for only by dominated convergence theorem, dominated convergence theorem. Okay, okay, nice. Yeah, and then yeah, so dominated convergence theorem, why? Because So actually, so this is bounded, right? So this is bounded by some integrable function. This is bounded by some integrable function, and then just by dominated convergence theorem, so you can like think like you can swap this integral and summation, infinite sum. So now from here, okay, so this 1 by 2 pi integration minus pi to pi, and here this fx equals to, so you here pr theta minus x, this is a function of theta minus x, you can write, and dx, and this is the convolution formula. So 1 by 2 pi f star pr theta. Okay, and where pr theta equals to minus infinity to infinity, not k, just you can write instead of k in r to the power mod n e to the power I n theta. So yeah, so this is called actually Poisson kernel, which is called Poisson kernel. Okay, now one thing we like we want to deduce further, so we want a closed form, we want a closed form for this. So this is like, this is sum, so like we need a closed form, so to understand clearly. Okay, yeah, so basically this closed form comes from, so closed form of pr theta. Okay, so pr theta is your this sum n equals to minus infinity to infinity r to the power mod n e to the power I n theta. Okay, and now what you will do, so we can split it like this, sum n equals to 0 to infinity r to the power n, when n is positive, so n is n, and e to the power I n theta. But when n equals to 1 to infinity, so when n is negative, so r to the power minus n e to the power minus n theta. And then n equals to 0 to infinity r to the r I theta to the power n plus n equals to 1 to infinity r okay, e to the power I theta to the power minus n. Actually no, okay, so here instead of this, r to the power minus a e to the power minus I theta to the power n, and this equals to n equals to 0 to, not r to the power, sorry. So here I am like confused. So that should be also r to the power minus n, right? Okay, so when n is your negative, yeah, that should be also, so r to the power mod n is it there, Oh, so yeah, sorry. So mod n is there, so always this is positive. So it should be r to the power n. Okay. So when n is negative, so okay, it should be. And then, so if we take omega as r to the power I theta plus omega bar, okay. So here we can start this from n equals to 0 to infinity, and this is omega bar to the power n. So that's why, so we are multiplying omega bar, extra omega bar, and because we started the series from n equals to 0. Okay, so omega is your r e to the power I theta, and now compute this. This is 1 by 1 minus omega, and this is omega bar by 1 minus omega bar, and then just multiply it. So 1 minus omega, 1 minus omega bar, and 1 minus omega bar plus omega bar 1 minus omega, this 1 minus omega mod omega square, and 1 minus this, basically this is your 1 minus omega bar plus square. Okay, this is we can write like this: 1 minus omega bar, not omega bar. So you are sort of multiplying 1 minus omega time 1 minus omega whole bar, right? So omega square. Okay, so now if we put omega equals to r to the power I theta, so mod omega is your r, so 1 minus r square, and here if we calculate like what is 1 minus r to the power I theta square, so 1 minus r to the power I theta times 1 minus r to the power minus I theta, so this is nothing but 1 plus r square minus 2r cos theta minus 2r cos theta. So this is the closed form of, so PR theta equals to 1 minus r square divided by 1 minus 2r cos theta plus r square. This is the closed form of Poisson kernel. Okay, now let us see some your properties of Poisson kernel that are also in exercise in lecture notes. Okay, properties of Poisson kernel. So first property is your very simple, this minus pi to pi PR theta d theta equals to 1. Number 2 is your Poisson kernel is always non-negative for all theta belongs to minus pi to pi, and R is your 0 and close 0 open 1. 3. The norm 1 is 1, and then 4. Integration delta less than mod theta less than pi mod pr theta d theta goes to 0 as r tending to 1. Okay, so these are some properties of Poisson kernel, and we want to prove this. Okay, so first is very simple. 1 by 2 pi minus pi to pi p theta d theta 1 by 2 pi minus pi to pi n equals to minus infinity. Now put the summation formula for PR theta e to the power in theta d theta. So this is 1 by 2 pi, and here also we can swap like this infinity r to the power mod n integration minus pi to pi e to the power in theta d theta. Okay, so e to the power in theta d theta, and this is this integral is 0 unless n equals to 0. Okay, so this integral basically minus pi to pi e to the power in theta d theta equals to 0 if n not equals to 0. Okay, this is simple proof. Just you can check it and show this 1 by 2 pi this holds so this will survive like only when n equals to 0. So from here this integral will give 2 pi, and this sum n equals to minus infinity to infinity, this is 1. Okay, is there some mistake? Yeah, sorry. So this otherwise this whole thing is 0 if n not equals to 0. So this r to the power 0 will be there, so this whole thing is 1. Okay, so what we are getting finally 1 by 2 pi minus pi to pi this PR theta d theta equals to 1. Okay, so this PR theta is basically your Poisson kernel. Okay, and next what we want to show, this Poisson kernel is non-negative. Okay, so again PR theta equals to, what is the close form, 1 minus r square 1 minus 2r cos theta plus r square, and how this is like positive for this is not positive, this is non-negative. Okay, So for okay, wait, r belongs to 0 1 and theta belongs to minus pi to pi. Okay, let's see. So this 1 minus r square is always a greater equals to okay, so r is in between, like minus 0 to 1, right? So r square is also 0 to 1, and so this is basically 0, greater equals to 0, no problem. And in numerator 1 minus 2r cos theta, so you can manage it, right? So 2r cos theta plus r square cos square theta plus r square sin square theta, and 1 minus r square, and this equals to nothing but 1 minus r square 1 okay, so 1 minus r cos theta whole square plus r sin theta whole square, and this whole thing, this is like positive, right? Not positive, so you can like say is non-negative, so whole thing is non-negative. So PR theta is greater or equals to 0. Okay, we already just proved, right? 1 by 2 pi integration minus pi to pi PR theta d theta equals to 0. So yeah, and PR theta greater equals to 0. So mod PR theta is nothing but just PR theta. Okay, so this norm 1 PR, this norm, this is what? This is basically 1 by 2 pi minus pi to pi mod PR theta d theta, and this is nothing but only PR theta 1 by 2 pi minus pi to pi PR theta d theta, that is 1. We already proved in 1, right? Yeah, so 1 is done, 2 is done, 3 is also done. Okay, so 4 I need to check. Okay, so now fix delta greater than 0. What we need to prove actually? So for any delta greater than 0, this integral when your mod theta that will be greater than delta and less than pi, then as r tending to 1, this integral goes to 0. Okay, and delta, we fix delta greater than 0 with delta less than theta mod theta less than pi. And now okay, simple, so we can write 1 minus 2r cos theta plus r square, this is equals to 1 minus r whole square plus 2r 1 minus cos theta. How? Because just we are adding and subtracting 2r. Okay, and this is simple, right? So what is your PR theta actually? PR theta is your 1 minus r square 1 minus 2r cos theta plus r square. Okay, and in denominator this is this. Okay, okay, so here what we want to do, like here mod theta is basically greater than delta. Okay, so if we like want to replace, so if we replace this theta by delta, then our inequality should be less equals to 1 minus r square 1 plus r square minus 2r cos delta. So we just replaced this theta by delta. Okay, and your delta greater than mod theta. Okay, and now, okay, and also this holds on, not always. This should be less than pi. Okay, so you can, like, graphically you can check it. Okay, and now 1 by 2 pi integration delta less than mod theta less than pi pr theta d theta, that is basically less equals to 1 by 2 pi delta less than mod theta less than pi 1 minus r square divided by okay, sorry, one thing I made a mistake. Okay, uh, this is how I cannot do. Okay, so yeah, from here we can do, because we need positivity also. So this is less equals to basically 1 minus r whole square plus 2r 1 minus cos delta. Okay, so 1 minus r whole square plus 2r 1 minus cos delta. Okay, 1 minus r whole square plus 2r 1 minus cos delta d theta, and less equals to, okay, so from here basically one can conclude this tends to 0 as r tending to 1. Okay, yeah, so finally we just got this integral goes to 0 as r tending to 1. Okay, hi Prathivan, right? So can you listen me, right? Hi Prathivan, am I audible? Okay, so in your assignment, hi.
Hi.
Yeah, so yeah, actually I just discussed some properties of Poisson kernel. Okay.
Okay.
Yeah, you studied, right? Poisson kernel, Phasor kernel.
Yes, Professor.
Okay. So yeah, so just I discussed first Abel summation formula. Okay, and then so how like this Poisson kernel is coming. So I just discussed about this, and so these are like Poisson kernel, and then we found this closed form by adding this all sum, and next we discussed some properties, and first property is that basically if you like integrate over minus pi to pi pr theta d theta, that is nothing but 1, and next property is uh, pr theta greater equals to 0. Okay. And
Okay, Prof. Carry on.
yeah, and third property is basically norm 1. Norm 1 means you know, right? So this integral mod PR theta d theta is 1. And fourth property is basically this integral when your theta mod theta greater than delta with this interval, so this goes to 0 as r tending to, so sorry here, so r tending to 1. Okay. Okay, so you registered this course or not?
Yes, Professor. I have registered in this course.
So okay, so you want to like give so you want to give the exam.
Yes, Professor.
Okay, good. So then join every day. So okay,
Okay. Okay.
okay, okay, okay. If you have any problem, you can ask me anything, anytime. Okay,
Okay, Professor.
okay, good. Okay, so okay, now you can mute your mic. Okay,
Okay. Thank you, Professor.
okay, okay. So now next we can study poison proponent. Hmm. Okay, so there is a problem related to your um, to find the limit of a sequence. Okay, so like that, so limit n tending to infinity n factorial divided by n to the power n plus half e to the power minus n. Okay, so how to find this limit? Do you have any idea how to find this limit?
Sorry, Professor. My screen is very small. I'm in traveling.
Oh, you are traveling.
Just
Okay,
I'm,
okay, no problem.
just
So
I'm
this
away in
kind of,
Mumbai.
okay, okay, no problem. So this kind of sequence, where this n factorial is appearing, okay. So here you cannot like find the limit directly. So, so here you can use some special formula, some approximation formula, Starling formula. Okay, the Starling approximation formula. What it says n factorial n to the power n e to the power minus n root 2 pi n for n very very large. Okay, so as n tending to infinity, this holds. Okay, no problem. As n tending to infinity, this holds. So you just put this the value of n factorial here, and you can find easily. Okay, I am not going to solve this. Okay, this is an assignment problem. Okay, okay, no problem. So next, uh, I want to discuss another problem. Okay, so this is about direct sequence. Okay. Mm, yeah. So direct sequence. Okay. we call a sequence of function qn on minus pi to pi a direct sequence if qnt greater equals to 0, qn minus t equals to qnt, and third property should be 1 by 2 pi integration minus 2 pi to pi qnt dt equals to 1. And on fourth property is basically for each epsilon greater than 0 and delta greater than 0, there exists n belongs to n such that for all n greater equals to n, this 2 minus pi to pi qnt dt plus delta to pi qnt dt is less than epsilon. Okay, so why it is important? Okay, there there is theorem let f be, wait a minute, okay, so let f be a continuous function minus pi to pi, and let qn be a direct sequence. Then qn star f converges uniformly on minus pi to pi as n tending to infinity. Okay. Oh, okay, sorry. Converges uniformly to f. To f. Okay. So proof is simple. So basically, see, given a continuous function f, so so you just there exists a sequence of function. There, first of all, given a continuous function f on the interval minus pi to pi, and then there exists a sequence of function which converges uniformly to f. Okay, so that's why this direct sequence or sequence of function is important. Okay, so let's see how it is working. So hn equals to qn star f. Now hnx minus fx, this is equals to 1 by 2 pi minus pi to pi f of x plus, sorry, so this is, yeah, so your x minus t minus f of x times q and t dt. So why? Because for fx you can write it like this, because integration minus pi to 1 by 2 pi minus pi to pi q and t dt is 1, because of this actually, because of this. So fx is nothing but this. Okay, so now let epsilon greater than 0. So one thing, f is continuous on a compact subset of R, right? So f is uniformly continuous on that set. So f is uniformly continuous on minus pi to pi. So then what is the definition of uniformly continuous? So there exists delta. So for every epsilon greater than 0 there is delta such that mod of fx minus t fx epsilon by 2 whenever minus t delta, also delta less than mod t less than pi q and t goes to q and t dt goes to 0. Okay, has entered into infinity. So from here there exists n belongs to natural number such that for all it equals to n 1 by 2 pi integration delta mod t less than pi q and t dt less than epsilon divided by 4 norm of infinity. So actually, so we need this letter, so that's why for adjusting, so we are taking here. Okay, how it is coming, we'll check. So now 1 by 2 pi integration delta less than mod t less than pi okay, so mod fx minus t minus fx q and t dt less than 2. So yeah, so this is basically, you know, subnorm. So this mod fx minus t minus fx, this is basically 2 time mod of fx, sorry, norm sub 2 times subpimum of mod of fx. So this is basically 2 times norm of f infinity. Okay, so that's why, so this is 2 time norm f infinity time epsilon to the power. So yeah, so when you are taking like a subnorm, so this integral is your epsilon by 4 times norm of infinity. So this is epsilon by 2. Okay, and okay, so for this interval this is epsilon by 2, and for this interval 1 by 2 pi mod t less than delta mod of fx minus t fx q and t dt this is actually, yeah, from uniform continuity. So this is bounded by epsilon by 2, and this one by 2 pi integration minus pi to pi q n t t t. This is 1. So yeah, so finally you are getting this is epsilon by 2. And now for whole interval minus pi to pi, okay, thus hn(x) minus fx is less than epsilon for all n greater equals to n, and for all x. Okay, so like this. Okay, so for direct sequence, so this holds, right? And so as a corollary, as an corollary, let f be a continuous function on t, not t, just you can say it minus pi to pi and pair theta is the Poisson kernel, then this f convolution pair converges to f uniformly as r tending to 1 minus. Okay, okay, so now let us see some another thing. Okay, then let us discuss something about phasor kernel. Okay, so what is phasor theorem? Suppose f fx is a periodic, not periodic, at least 2 pi periodic continuous function on the real line, and Sn fx is the n partial sum of the Fourier series of fx, then limit n tending to infinity 1 by n plus 1 is 0 fx is 1 fx plus Sn fx equals to fx. Okay, this is called phasor theorem. Okay, so the proof is already done in lecture video. Okay, so I'm not going to prove it. Okay, so but I want to discuss about some properties of phasor kernel. Okay, so how it is coming? So yeah, so what is phasor kernel? Okay, so kn theta, this is basically 1 by n plus 1 times k equals to 0 to n dk theta. Okay, sorry, dk theta. What is dk theta? Dk theta is, if you remember, so this is Dirichlet kernel, and so yeah, 1 by n plus 1, this sum k equals to 0 to n sine k plus sine k, not only k theta. So yeah, k plus half theta divided by sine theta by 2. Okay, now we can deduce it. So this by this 1 by n plus 1 by sine square theta by 2, this sum, just we are multiplying sine theta by 2 in both numerator and denominator. Sine k plus half theta sine theta by 2 half times this. Sorry, cos k theta minus cos k plus 1 theta. One by n plus 1 square theta by 2, and this is if you just here find the sum. Okay, so this is nothing but 1 minus cos n theta divided by 2, and and finally n plus 1. So this is 2 times sine square in sorry, this is not actually n, this is n plus theta. Okay, so 1 minus cosine 2 sine square theta by 2, so 1 minus, okay, so sine square n plus 1 by 2 theta divided by sine square theta by 2. Okay, so this is actually phasor kernel tan theta. Okay, so similarly this kernel has some properties. Okay, properties of, oh sorry, okay, first property is basically kn theta is your non-negative for theta belongs to minus pi to pi, and n is basically it's to capital N belongs to n, and 2 norm kn 1 norm 1, and number 3 is limit n tending to infinity delta t less than pi kn theta d theta equals to 0 if delta greater than 0. Okay, so these 3 property we want to discuss. Okay, so first one is very simple, we already done it, right? We already have done it. So we have kn theta is sine n plus 1 by 2 theta divided by sine theta by 2 square, that is greater equals to 0, and 2 1 by 2 pi minus pi to pi tan theta d theta. Okay, so this is positive, right? So this gain norm 1 is this. Okay, and this, and gain is positive, so this 1 by 1 by 2 pi minus pi to pi gain theta d theta. Okay. Actually this is simple, because gain theta is your nothing but 1 by n plus 1 minus pi to pi, this sum k equals to 0 to n dn dk theta d theta. Okay, k in theta is basically this 1 by n plus 1 and this times this sum, and this is Dirichlet kernel. And now, so here, since this is a finite sum, so 1 by 2 pi, we can just swap the integral and series. So k equals to 0 to n, so integration 1 by 2 pi minus pi to pi dk theta d theta, and this is actually 1, so this 1 by n plus 1 and this whole thing is 1, so that's why k equals to 0 to n 1. So this is nothing but n plus 1 divided by n plus 1, this is 1. Okay, and so what we are getting, the norm of gain, this is 1, norm 1 is 1. Okay, and now what is number 3? So we want to so that limit tending to infinity delta less than mod theta less than pi gain theta d theta equals to 0 if delta greater than 0. Okay, so one thing also necessary. So in lecture video, the gain theta is defined by this only, actually by 2 pi times. Okay, so but here I am taking like only this 1 by n plus 1 times this. Okay, so that's why in lecture video, so the integral is basically minus pi to pi gain theta d theta is 1. Okay, no problem. Okay, how to show this? Fix delta greater than 0, then for delta less than mod theta less than pi, okay, less than pi, so delta is your positive, right? Delta is positive. So your sine graph is like this, 0 to pi. So this theta positive, basically 0 to pi. So theta is like this. Okay. So for this, one can say sine square theta by 2, this is bounded by something constant depend on delta. Yeah. The integration delta mod theta less than pi kn theta d theta equals to 1 by n plus 1 integration delta less than mod theta less than pi sine square theta by 2 sine square theta by 2 d theta 1 by n plus 1 delta is to 0 s intending to infinity. Okay, so finally delta, okay, less than mod theta so by kn theta d theta 0 when delta must be positive. Okay, so these are some properties of phasor kernel. Okay. So from these also one can prove the trigonometric polynomial are dense in L2. Okay, so this is an application of Phasors theorem. Okay. Now we move to something related to Kroneker's theorem and Wheel distribution. Kroneker's theorem and equidistribution. Theorem. So first of all, we just see what is Dirichlet theorem. Okay. Dirichlet theorem. You suppose alpha is an irrational number. Then consider the sequence of number alpha 2 alpha 3 alpha. So where this bracket is basically fractional part of dot. Okay. So, so this number in the list are all lies in 0 to 1 because the fractional part lies in 0 to 1. Okay. So this is like 1, and also let k alpha equals to L alpha and k less than L. Okay. Then k minus L alpha equals to k alpha minus L alpha. But this means alpha is a ratio. So this is basically 0, right? So alpha is a ratio of two integers. So alpha belongs to Q. But this is contradiction, right? We assumed alpha is your this is contradiction. So yeah, so this sequence, so because we assumed alpha is irrational, so this is contradiction. So this sequence now, the sequence has some limit point, must have some limit point. One has some limit points, at least once. And in this regarding, Kroneker's theorem asserts that 1 is dense in 0 to 1. Okay. So there is simple proof. Okay. Yeah, so proof is basically, so we know, right, h m plus n alpha, m n belongs to z, is dense in R. Okay. So h is basically here for 0 1, so it would be dense in 0 1. So our aim is to prove thus this set H intersection 0 1 is basically the set of numbers. Okay. So one thing is clear, right? So this all the n alpha, this lies in this set because H is like that. So H is your m plus nz, n alpha, right? Okay. So one sided is true. Okay, let's see for other side. So let x belongs to H intersection to 1. So x is basically your x, because this is a fractional part, right? So yeah, alpha is also not an integer. So 0, alpha is not 0, alpha is not 1. Okay, and this is m plus n alpha, and this is m plus n alpha plus n alpha, and from here okay, so from here what we are, yeah, so from here m plus n alpha is 0, and from here x equals to n alpha. Okay, and basically x belongs to n alpha. So yeah, maybe 1 alpha, 2 alpha, 3 alpha, and so on. So this is h is precisely same as h intersection 0 1 is precisely same as this set alpha, 2 alpha, 3 alpha, 3 alpha, and so on. Okay, and yeah, and from these we have one important theorem related to a subgroup of R. Suppose not suppose, so basically it says every subgroup of a of R is either cyclic or dense in R. So the proof is available in lecture notes, you can see. Okay, so using this result, you will have two like you can solve two questions from assignment. So which of the following subgroup of R are cyclic? So yeah, so let's check. If the set is not dense, then it must be cyclic, and if the group if the subgroup or the set is dense in R, then yeah, it must be non-cyclic. Okay, so from this result you can check. Okay, so there are several things. So the question is basically an assignment. the set all finitely generated subgroup sorry subgroups of Q and all finitely generated subgroups of R. Yeah, so you can check whether this is dense or not to because to check a cyclic so to check whether it is cyclic or not, it is difficult. And also you can check here the denseness easily, and for these two things you can like you can use uh, some results from group theory to show these are cyclic or not. Okay, so up to this I wanted to discuss today. And yeah, next okay, so we will discuss uh, another thing, yeah, interesting thing, well equidistribution theorem. Probably next day I will discuss it. Okay. Okay, so today I stop here. And so yeah, if you have any question, then you can ask. Okay.